Before I go into the understanding of how to apply the PID controller into certain systems, I'll just briefly talk about the definitions in a short way, such that the proportional control, if you remember, is a contribution based on its instantaneous error. Alright, because if you have a signal over here, this is your reference signal, REF, alright, and you have to compare with your output. So your reference minus your output will becomes your error, right? And therefore this error is instantaneously set into your controller. Alright, and therefore is directly contributed based on your instantaneous error. Because once you input your error, you will straight away output as times 3 or times 4 of your error. You no need to alter or change the data or things like that based on how the integral controller and the derivative controller use. Alright, so it's instantaneous contribution. Alright, and it's a limited, maybe I should go on. It's a limited performance and non-zero steady state error, because limited performance means that once your gain is high, you'll be very oscillatory, right? If you were to just remember back, if you have a low gain, you somewhat becomes like this, and this is the steady state that you want, your response. Maybe you want your response to be 1. Alright, should be fine for a normal low gain. Alright, but it is low because your gain is low. If your gain is low, then your performance will be slow. Alright, therefore it's limited performance. If your gain is high, and therefore you'll just spike up and be very oscillatory, and then you'll just die down to a steady state that is higher than what you want it to be, because we want it to be 1, but when it goes to this steady state, it becomes something else, maybe 2. So this is the steady state error that we're talking about. Alright, as for integral control, you actually somewhat output your accumulated error. Alright, so you accumulate all your error and then you sum it up and compare with your reference signal and things like that. And it's a slow process, so it's not very good. And then it forces your steady state error to 0. Alright, and therefore if you're talking about certain responses, even if it's a low gain, something like this. If it's a high gain, you're just something like this, but you'll still go back to here. Alright, if it's a damn high super gain, then maybe something like this, and it goes down. Alright, and also you will somewhat control your transient mode, alright, to be somewhat stable for your. So this means that you're not very oscillatory. Okay, and used for stat reference signal and disturbance. Alright, meaning that you're talking about the constant steady state error. You can use the integral controller, your I controller, to remove the constant steady state error. For example, if you input a low gain, it's something like that. This is your desired output as 1, and then you input a certain amount of high gain, and then it becomes like this for the proportional gain. Alright, for the P gain. So there will be a steady state error over here. But if you input our integral controller now, alright, it actually somewhat dies down and becomes like this. Alright, so your steady state error has been removed, but it's only for the state that is constant. If it's always constant over here, then you can use this method. If it's somewhat like an oscillatory, alright, then you're going to use the derivative control. Alright, because it kind of deal with the oscillatory part. This part over here is curvature, or your derivative part, your curvature. I don't know what I was saying, but yeah. And these are the things that I didn't go through in the last video. I thought that might be fairly useful to go through with you now. Alright, and therefore let's just continue back to what we are supposing to do, right? In fact, this whole thing over here is your what do I say? Your PID control. Alright, this, if you were to multiply this K in, is simply K. This for the proportional control. If this K over here is for your integral control, and the K over to this side is the derivative control. Alright, so it's the constants for them, but nonetheless you still require a certain TI and TD, somewhat dealing with your period and your time. Alright, by ensuring that your TI must be greater than your TD. Alright, this is the control law. Alright, you're going to control your thing you're gonna control your PID based on this law, ensuring that your TI is larger than your TD. As you can see, we have a TI to control and we have a TD to control, and therefore this thing over here describes a two degree of freedom of your thing. Because if you were to go back, where am I? This thing over here previously was a controller C over here, right? And we say that the controller C itself is a 1 degree of freedom controller to your plant. If you have a filter outside over here, you may have a second order degree of freedom to actually control your plant. But because we didn't talk about the filter, so we initiate to talk about the controller. So the controller within itself, we choose the PID controller, which uses the PI and the PD. So the PI and the PD, KI and the KD, has its own TI and TD, which talk about different frequencies gonna input with themselves. Alright, so you input one frequency, you input another frequency over at TI and TD differently. Alright, you're gonna change the thing in terms of 2 degree of freedom, because you can change this thing. This is 1 degree of freedom. You can change the plant with another degree of freedom, and therefore it's 2 degree of freedom. Or in other words, you can change with a frequency of what omega is equals to 1, you can change the frequency of omega is equals to 3. So you have 2 choices to put it in. Alright, so if you cannot change your TI, then you can change your TD. If you cannot change your TD, you can change your TI. So you can somewhat do things in a more fairly useful manner. But however, it's more laborious, because you're gonna have more items, and it's more expensive to create. Alright, but these are the things that comes with designing. So now, if my T1 is equals to TI is equals to 10 second, which corresponds to 0.1 radian per second. Alright, so this is the frequency for your integral. Alright, as you can see, your TI is larger than your TD. Your TD is 0.01 second, your TI is 10 second. So this is the rule, TI must be larger than TD. Alright, so please remember that your integral must be larger than D. Or in other words, you can remember by PID, so I must be greater than D because it comes before him. Alright, things like that. For this example, if we were to input this amount of T, 10 second and 0.01 second, what we can see is this graph over here. And what is the purpose of this graph? Why is it the trend is like this? Alright, typically normal responses, they'll just spike out, and eventually they will die down, right? And we want to increase its overall maybe a steady state is something like this. Alright, so it all go all the way like this. Alright, and we want to increase our steady state. We want to increase our steady state over here. So therefore we input this particular controller such that at this point, because this point is growing up, right? This point is growing up. Therefore, our point over here, you no need to increase anything because this thing is going up. So we no need to increase anything. So we just let it down first. And up till this point, where this is the peak point, you don't want to, because it's already very high, you don't want it to increase anymore. So you continue to go down again, and become stable all the way up till when it reaches the frequency that you want. Alright, at this point of time, instead of going downwards, your this part actually pull your this pin upwards, so you actually somewhat go in this direction, therefore it goes up. So from this part to this part over here, you somewhat tries to increase your this thing over here to this line. Alright, so you somewhat increase your steady state response, so therefore you have a better gain and a faster responses and things like that, and therefore this shape over here is being utilized in such of a manner. And this is for the gain system for the body plot. Alright, it's for the gain. And if you remember, we have a face plot also, face body plot, and it's in terms of this shape. I don't know how to explain, but just for you to take note. Alright, and therefore you may see some other PID controller shapes like this, or it may be something like this also. It depends on how much you want to deal with things. Seems like a lips, so if I were to draw this nose and I were to draw this eyes, wow, cool. Anyway, just an example, you have some plant controller transfer function and your controller C, which is your PID controller, with your whatever inputs over here. Alright, just simply sub it in. Alright, and therefore it results in thing over here, So this one, as I said just now, this shape is your controller, your PID controller shape. Alright, it can be this shape, right? And therefore this thing is somewhat more realistic lah. And then you have your CP, your overall closed loop transfer function. Okay, now I just go on with the plant first. Initially the plant is response is something like this only. Alright, it's somewhat lousy, and you want to increase, right? So when you increase the gain, you use your PID controller, and therefore this PID controller actually increases your this plant to this red line over here. So you somewhat increase overall. Alright, I hope that you somewhat see that coming. And therefore, as for the phase margin, as you can see, is something different. For the phase is at first the plant was like this, and then you input your controller's gain such that you improve your phase margin to be 90 degrees. Alright, to be somewhat pretty I think stable, I don't know, but yeah. As for the equation to sub in, I'll highly recommend you use this equation. Alright, K over S and then TDS plus 1, this one. So you sub in your TD and your TI, you have some form of your controller's transfer function. Alright, and this can be seen by over here. Alright, this is 100S, maybe I should crop them up together, hold on. So this part over here, KS, is 100S. And then you sub in your particular TD, alright, you have 0.01S plus 1, and then S plus your 1 over TI is some values over here. Alright, so therefore, I'll highly suggest that you take this equation to use it as a general equation. Alright, but nonetheless, you can also deal with these things. Alright, so these are the things that you may need to consider in your stuff. Alright, and lastly, I'll just quickly touch on the slides, because it's just a few things that I want to explicitly define. Is that when we design our PID controller, we are designing the frequency response. We're going to design your frequency, because we'll input your frequency, if you still remember just now that the particular examples. Alright, it's over here where you're going to input your frequency. Where's my frequency? Good job. Wait, this one over here, 100 radian per second is 0.01 second, 0.1 radian per second is your 10 second. Alright, you wonder how to convert. It's simply because this is 0.1 radian per second. Alright, you want to set it to 1 second, and how do you set it? Right, so you have to times 10. So when you times 10, you have 1 second over here. Am I right? Sorry, we are in terms of 1 radian. Alright, we want it to be 1 radian. So therefore, 0.1 radian times 10 seconds is equals to 1 radian. Alright, we want everything to be 1 radian. I don't know why I say 1 radian, but it's 1 radian. But anyway, so this thing over here, you just sub in over here, and then if it's 100 radian per second, right, you're gonna sub in 0.01 second, so that it becomes 1 radian also. So therefore, you sub in this 0.01 over at the side. Alright, these are the little small stuff, that's why I want to go through with you, at least in a faster way. Now next, here you can see that we're talking about the frequency now. Alright, this changing of the frequency, if you input different frequency, you somewhat gonna loop shape your system. Or you're gonna modify your shape of the loop gain, meaning your Nyquist plot. If you still remember, you're gonna change the shape, maybe something like this, or maybe like this, whatsoever. Happy can already. But anyway, it's to design your performance. Alright, to improve your performance so that you can do faster, and you have a larger bandwidth so that you can take in more frequencies to do things. Alright, robustness also with respect to stability and performance, because you want your system to be stable also. That's why we want PID. Alright, PID, everything is stable and nice. Not very nice, but at least something nice. And just to touch over here, this real axis over here all the way is your gain margin. Alright, while this line over here that all the way goes into this thing is your phase margin, because talk about the imaginary axis. Alright, so this is the real axis. So when you take a look, you just simply check it out over here. Alright, this is the real axis. And as this particular point is your gain crossover. Alright, because your Nyquist plot is somewhat like this. Alright, over like this. So you're gonna so your radius of one circle somewhat over here. So when you reaches the particular real axis, alright, this is all the way down here, so it's over here. So this thing over here is your crossover. and therefore it's reflected over at this side over here. Something for you to know lah, alright, since she say that. And at this point where it touches the negative, I mean the 1 radius, alright, this 1 radius over here, this point, alright, you're gonna talk about this phase crossover. Is it? Yeah, it's a phase crossover. Right, so it's this point over here. Alright, I don't know how the crossover will do, but yeah, let's continue see how. So I think anything beyond this is actually unstable. Anything beyond this is unstable. I don't know. I'll leave you to think about it, because this point over here, if you just take a look, is a point at the negative, at our radius 1, alright, which is at this point over here. Alright, while our real gain crossover is at the real axis and also at the 0.1 part, I would say. Alright, I don't know, I'll just leave you to think about it, and that I think that's all. I shall see you soon in the other videos.